Okay, before start today's class, can you see my PPT slide? The lab number 2. Okay. Okay. So before starting today's class, I will briefly explain about the lab number 2. So it's a design lab. So actually the final goal of our design lab assignment is to implement a pipeline processor. It's a RISC-V pipeline processor. So actually in the chapter 4, we learned how the single cycle processor can be designed. So we start from the how instructions are executed in RISC-V processors, and then we categorize the required steps for executing RISC-V instructions. Then based on these steps, we define the data path elements. So what are data path elements? So those are some hardware resources or hardware components that are required for processing some data, or some element required for changing the result of the instruction. So, and then in a single cycle processor design, we connected some input-output port of a data path element. So that means that we just define the data flows between these data path element. Okay, so that means the hardware component. And then finally, we define the required control signals for each data path element, and then we build the control unit. Okay, that's how to build the single cycle processors. Okay, and then this is the second design lab assignment. So the goal of this second design lab is to build data path element required for our RISC-V processor design. Okay. Okay. So I mentioned that the goal of this assignment is to build a data path. That means the data path element. So in this assignment, you are requested to design register file, instruction memory, and data memory, and ALUs. So those hardware components are required for executing basic RISC-V instructions. Okay. So we learned about the instruction fetch. So which data path elements are required for this instruction fetch? So we require the program counter registers and instruction memory. So, and then in this lab assignment, you are requested to design instruction memory. So during the class, I explained the operation of memory. So what is the operation of the memory? If an address is given to a memory, then the memory generate output data that is pointed by this input address. Okay, and then as you know, the instruction memory does not have any write port. So that means that just these instructions are just stored inside of instruction memory. So if an address is given to this instruction memory, then instruction memory just generate the data. That is the instruction. But this is, so you are requested to design just a memory. So instructions are not provided for this lab assignment. So actually the third lab assignment is to build a single cycle processor. So, and then for the third lab assignment, some instructions will be provided. But for this second lab assignment, we will not provide any instructions. So just assume that some data is stored in the instruction memory, and then if certain address is given to the instruction memory, and then the data can be read out from the instruction memory. Okay, and that's it. So as I mentioned, so if you see that this figure, that you can find that instruction memory just has 2 ports, the one input port for the read address, and then one output port for instruction. But in the I believe I provided the skeleton code for database elements, right? Okay. So if you see that this skeleton code, then the input and output ports are defined. So this is the module name, it's the IMM. And then as you can see, in the module, you can find the input and output port, right? And then, so this part defines the width of input and output ports, okay? So as you can see, the width of the address is defined here, the IMM address width. And then as we learned, the width of the instruction of RISC-V is 32 bits, okay? So that's why DL is the 32-bit data, okay? And then this is the input and output. And then how about the register file? So register file has 2 input data ports. That means 2 read register ports, and then 1 write to register port, and then 1 write data port. Okay, so these are input ports, and then also, as we learned, the register file has read write control port. So it's a control input for the register file, and then there are 2 data output ports, so read data 1 and read data 2. And then as you can see, so we also provide the skeleton of the register file, and then module name is reg file. And then the width of a register, a single register is defined here, is 64, because we are learning 64-bit processors, okay? Also, so these register input and output ports of register files are defined here. But if you read the system verilog file, then you can find these comments. So I wrote these comments here. So it's about the write operation. So actually in our in the class, we learned that the register file does not have any clock signal input. So that means that the register file is not sampled by clock signal. But if you read the lab assignment document, then you can find why our design requires clock signal input. Okay, so it is because this register file supports the internal forwarding. So that means that if the data is written to the register file, then this data is forwarded to the input, then the read out port of the register file. If the input and that means the read register number and write register number is equivalent. So, but problem is that in the combinational logic, if the feedback loops are generated in the combinational logic, then the updated values are infinitely updated again and again. So actually, in the combinational logic, we need to avoid this feedback loop. Okay. So It's like add x1, x1, x1. So that means that the the result of x1 plus x1 is updated to the x1 again. And it's the possible instruction in RISC-V processor, right? Right. So it's like x1 multiplied by 2. Okay. But if the right data is not sampled by this clock signal, that means that the register file is just a combinational logic. So x1 plus x1 is repeatedly updated to the x1. So what's the problem? x1 is updated. So x1 becomes the x1 multiplied by 2, and that is the new value. And then in the system Verilog, if the new value is given to this combinational logic, then this combinational logic works again because input values are updated. So in the first class of the chapter 4, I explained that combinational logic is something like y equal fx, and then x means just input signals, and then if x is changed, then output is changed after some delay. Okay, so if we just consider about the add x1, 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 then x1 is updated. So that means that the value of the x1 in this register file is updated. So that means the input values are changed. Then this register file works again. Then the output, what is the output? It's x1. So x1s are also generated. And then the x1 plus x1 is performed by ALU, and then new result are generated. And then this is feedback to the register file. So the updated value is updated again, again, again. It's why we require the clock signal for this register file, actually for write operation. So please read this comment, okay, and then try to understand why we need this clock signal input for register file. Okay. And then data memory is also simple. It's similar to the instruction memory, but the one difference is that data memory has the write data port. Okay, so data memory has two control inputs, and then mem write and mem read. So as you can see, our data memory also has these input and output signals. So these skeleton codes are also provided for this second lab assignment. And then as you can see, this data memory has also clock input. It's the same reason for the register file, okay? So actually, the write operation of this data memory is sampled, synchronized by clock signal, okay? It's the same reason for the register file. So in the skeleton code, you can find the write operation, and then write operation has this always statement. So, and then this always statement is sampled by positive edge of clock signal. Okay. So write operation of the data memory, and then ALU. So this is the ALU we learned in the class. Okay. So this is the ALU control signals, and then based on the ALU control signals, then the function of the ALU is determined. But in this lab assignment, this ALU need to support the 4 branch instructions. So actually, this was the question in the midterm exam. Okay. So I will. So as you can see, the new ALU has sign output port. Okay, so and then I believe you can understand why this sign output port is required, because the ALU need to support the PQ, PNE, PLT, and PGE. So actually, we can easily compare two values with the subtraction operation. Okay, but if ALU just supports the BQ instruction, we just need the zero detection. So that means that we can just detect the A equal B. Okay, but so we can also easily implement the BNE with this zero output from the ALU, but for BLT and PGE, then we need to check the sign bit of the result. And I believe it's very simple. Okay, so new ALU has this sign bit output. So as you can see, the input and output ports of the ALU has this size 0 bit and the sign bit and the result. So you can find the in1, in2, that those are the input operands for ALU, and then you can find the ALU control signal. So, and then actually the operation of the ALU is defined like here. So, see, actually the same to the ALU design appearing in our textbook. Okay, but because this ALU need to support these three other branch instructions, ALU just needs the one sign bit output here. Okay, and that's it. Okay, do you have any questions about this lab assignment? Okay. Okay, good. I think everyone can everyone can do the second lab assignment easily, hopefully. Okay, let's move on to our today's class. Where is the okay? In the previous class, we learned about basic of pipelining design, and then in the previous class, we learned about the hazards of processors. Okay, I think I mentioned these hazards are very important. Why? What is the hazard? What's the meaning of the hazard? So meaning of our hazard is an event that wastes clock cycles. So I repeatedly mentioned that, processor, we assume that one instruction can be executed every clock. But for some reasons, this assumption can be broken because of hazard. So there are three kinds of hazards: structure hazard, data hazard, and control hazard. So these three kinds of hazard are categorized by the reasons of hazards. Okay, so you need to understand the reasons of hazard. So if we know the reasons of hazard, then we can develop solutions for avoiding hazards. So why do we need to avoid hazards? To improve performance of processors. Okay, because if a hazard happens, the clock cycles are wasted. So that means the performance is degraded because the execution cycles are increased. Okay, so there are three kinds of hazard based on the reasons of hazards. the structure hazard and data hazard and control hazard. So structure hazard are happened because of lack of hardware resources, but in this course, we do not learn about the structure hazard, okay? Because this is the pipeline design. Also, we already split the memory into instruction memory and data memory. So I explained why we need to split instruction memory and data memory, okay? Then data hazard. Data hazard are caused by data dependencies in instructions, okay? What is the data dependencies? The result of former instructions are used by the next following instructions. So those are next instructions. So because of these data dependencies, and then if the data is not ready inside of a processor, then the next instruction need to wait until these required operands are ready in the processors, okay? So those are data hazard, and then control hazard. Control hazard are caused by waste of clock because of control instructions, like branch instructions, okay? These branch instructions change the next PC value. Actually, we assume that the next PC is the PC plus 4 for the RISC-V instructions. But if the branch is true, that means that the condition of a branch is true, then the PC should be target of branch. So that is not next PC. So instead of using PC plus 4, we need to calculate the target PC of the branch instruction. And then actually the result of a branch is reserved in ALU, that is the execution stage of the pipelining. And then so this resolution of the branch result is done as a late stage of the pipelining architecture. That's why. So if the branch result is true, then the target of the branch is updated to PC lately. So then we need to cancel the next instructions, and then because of this branch instructions, the clock cycles are wasted. So this is the control hazard in the pipeline process. So it's very important. So you need to understand why hazard happen in the pipeline processor, and then what are the reasons, that means the sources of hazard. Okay. Okay, so now in this time, we will learn how to implement, how to build pipelining processor. So in chapter 4, we learned how to build a single cycle processor. And then based on this single cycle processor, now we will learn how to build pipelined processor, okay? Okay, let's start from the single cycle processor. And then we learned that pipelined processor has 5 stages, the 5 stages of instruction fetch, instruction decoding, execution, memory, and write back. So just ignore these lines between each stages. So if we just see this processor design, then we can find that, this is just a single cycle processor. So when we learned about the single cycle processor, we learned how each stage, so each steps each step of single cycle processor works. Okay. So for example, for instruction fetch step, the PC is generated from the PC register, and then this PC values is given to the instruction memory. Then instructions come out from instruction memory. Okay, this is the instruction fetch stage. And the instruction decoding, the register files are accessed, and then the instructions are also decoded, and then control signals are generated. There is the instruction decoding step. And then execution, the ALU is used for performing instructions like R-type instructions or address generation of memory instructions. Also in the memory step, this data memory is accessed, and then the result of the instructions, as the final result, is written back to the register file in the write back step. Okay, so we can just split these steps required for executing RISC-V instructions. Okay, we can just split. So these are data path elements, and then data connections between data path elements. And then based on the steps we learned in the previous class, we can just split hardware components. Okay. Then how can we build pipelines? So what is a single cycle processor? Okay, what is the single cycle processor? Within one clock period, these 5 steps of executing instruction are performed. So that means instruction fetch, instruction decoding, execution, memory, and write back operations are done within one clock period. Okay, this is the single cycle processor. So, and then in the first class of the chapter 4, we learned that the basic digital system design looks like this. So between 2 D flip-flops, there is combinational logic. Then operation of combinational logic is done within one clock period. Okay, so if we just apply these, not definition, some basic analogy to a single cycle processor design. So that means that, so this is the combination. This is a combination. This is combinational logic for instruction fetch, and then another combinational logic for instruction decoding, execution, memory write back. So those are connected to each other like this. And then the operation of these hardware components or combinational logic is done within one clock period. Do you understand what I said? Then how can we divide these steps to 5 stages of pipeline processor? So we learned this is the basic design of the digital design. Then how can we split each step of this single cycle processor design? So I mentioned that this is the combination logic of instruction fetch. This is the instruction decoding. So also combination logic, execution, memory, and write back. And then this is the D flip-flop, and then this is another D flip-flop. we can just insert what? Insert D flip-flops between two neighbor steps. Okay, so this is the pipeline design. So actually, so this is called the pipelining register. Okay, pipeline is sometimes it's called the pipelining, or sometimes it's called pipeline register. So okay, pipeline register. And then, but actually, this pipeline register is just the flip-flops. What is the operation of the flip-flop? So this is the operation of the D flip-flop. Oops. So it's a clock. This is the D. This is a Q. So this is the input. So at the rising edge of the clock, this input signal is sampled, and then the output is maintained by this sampled value of input signal during a clock period, a single clock period. Okay, so that means the input value is temporarily stored in this D flip-flop. That's why these D flip-flops are called pipeline register. So, and then we already know that the register means the temporary memory that stores data. Okay. So how can we build the pipeline processor between two adjacent operation steps like instruction fetch and then instruction decoding, and then also we can define the combinational logic for instruction fetch. So that means data path element for instruction fetch step, and then this is combinational logic for instruction decoding step. And then between these combinational logics, we just insert D flip-flops or pipeline register, and then the output data of this combinational logic of instruction fetch step is sampled by this clock signal of D flip-flop. Then this sampled output, so it's a sampled data for this pipeline register will be maintained. How long? Will be maintained during one clock period of clock signal. And then, so that means that the input of this combinational logic in ID step is maintained during one clock period. Okay. So that means, so input is maintained. So input data is maintained during one clock period. So during this one clock period, the output of this ID step is generated by data path elements of the ID step. That means the combinational logic of this ID step. So output data is generated, and then this output data of ID step is also sampled by this pipeline register. Okay, actually the flip-flop. Understand? And then there is another combination logic for the execution stage. And then this is another combination logic for memory stage. And then another combination logic for write back stage. So this operation is done within one clock period. And then input and output of this combinational logic is sampled by clock signal using D flip-flops. Okay, so how can you build pipeline processor? So how can you build pipeline processor based on the single cycle processor? We can just insert pipeline registers between. It's a step of a single cycle processor, and then input and output of data path elements for each step are sampled by clock signal. That's it. Oh, it's done. We are done. So we learned how to build a pipeline processor, but we need to. So in the pipeline processor design, we need to match the timing of input and output. So actually, matching this input and output timing is a little bit tricky job. So we need to learn, okay? But the basic concept of a pipeline design is that between two neighbor steps, just insert D flip-flops and then input and output. So output of the previous steps is sampled by clock signal, and then this sampled data is provided to the next step, next stage of pipeline process. Okay. Okay. So in the pipeline architecture design, this is what happened? This is the instruction fetch stage. This is instruction decoding stage. This is execution stage, and this is the memory, and this is write back stage. And then these are the pipeline register. And then in order to this pipeline register is named as the neighbor stages of this pipeline register. So for example, this pipeline register is called instruction fetch / instruction decoding pipeline register, but we frequently use just this notation, instruction fetch just / instruction decoding. So that means, this means this is a pipeline register located between instruction fetch and instruction decoding stages. How about this pipeline register? This pipeline register is called ID / EX, then EX / mem / write back. Okay, this is the notation we will use in this course. Okay, so if I just mention instruction fetch / instruction decoding, and this means that this is a pipeline register between instruction fetch and instruction decoding stages. Okay. And then let's see how instructions are performed inside of a pipeline processor. So we can use the single clock cycle diagram or multi-clock cycle diagram. So in a single clock cycle diagram, we just show how instructions are performed during the single cycle period. So that means a single clock period. And then multi-clock cycle means that this diagram shows the operation of the instruction during multiple clocks. Okay, we just start from the single clock cycle diagram. Okay, so for the load instruction, like load x1, x2, immediate. So immediate and x2. So this is an example of load instruction, and then let's see how this load instruction is executed in a pipeline processor. And actually, it's simple. It's very similar to the operation of the single cycle processor. It is because the operation of the pipeline processor is just, so it's like splitting the steps of a single cycle processor. Okay. So during the instruction fetch stage, the PC is given to the instruction memory, then instruction is out from the instruction memory, and then the next PC is generated, each PC plus 4. And then in this pipeline processor design, you need to know that the PC is sampled by clock signal, and also this instruction fetch / instruction decoding pipeline register is sampled by clock signal. So this is the clock signal, and then during one clock period, this instruction fetch operation of this load instruction is performed. So at the rising edge of the clock, the PC value is out from this program counter register. Okay, so PC is out from here, and then this PC is given to the instruction memory. Okay, so instruction memory is here, and then after some delay, because this is a combinational logic, after some delay, like delta t, then what is out? Instruction is out from instruction memory, and this instruction is sampled by rising edge of the clock at this pipeline register. You understand? So I don't know if you understand or not, because I cannot see your face. It's not easy. Okay, this is the instruction fetch stage of load instruction, and then it's done. The instruction fetch stage is done. So what data is sampled by this clock signal, rising edge of this clock? So this data and PC. So PC is connected to here. So PC and instructions are sampled by this timing, the rising edge of this clock signal by instruction fetch and instruction decoding pipeline register. And that's it. So during the next clock period, so here, this instruction data is delivered to the register file. Okay. Also, the PC is also delivered here. So this is the instruction very next of the rising edge of this clock. And then the instruction is decoded, and then decoded instructions are given to the register file, like read register 1, register 2, blah, blah, blah. Also write register can be delivered. It's given to the register file. So actually, this is not correct design, but it's just the beginning of the so we are just learning about the instruction decoding stage. Just ignore that is incorrect design. Okay, so load x1, x2, and offset. So this is the read register 1 of the load instruction. So read register 1 is given to the register file, and then the base address, the data is out from the register file. Also, the load instruction requires the immediate data. So immediate data is generated by immediate generator within 1 clock period. Okay, so register file is accessed, and then immediate generator is performed within 1 clock period. And then at the rising edge of the next clock, so these are also sampled by clock signals. So the output of a register file and the output of the immediate generator are sampled by this pipeline register, instruction decoding and execution pipeline register. See? Then it's the same. It's a data is given to the ALU, and then the ALU results are generated within 1 clock period during the in execution stage. Okay, and the data is propagated to the next stage. So you need to know that these pipeline registers are sampled by clock signals. Okay, so this is the memory stage of the load instruction. So this load instruction at the memory stage of the load instruction, this address, so generated address are delivered from the ALU, but this is the sampled data. So it's just sampled by rising edge of the clock signal. Okay, so the rising edge of the clock, this address is given to the data memory, and then the data is out from the data memory. When around this, after some delay of the data memory, the output is out from this data memory. Okay, so address is given at this timing because this is the output of the D flip-flop, and then after delta T, the data is out from the data memory, and then this data is sampled by this rising edge of the clock. Okay, and then write back. So load x1, 0, x2. So this data, so data out from data memory is sampled by clock signal by memory and write back pipeline register. Okay, and then this output should be written back to the register file. So this is the destination register file, like this. And then what's the problem? The problem is that timing of this destination register file number and the timing of result of load instructions are different. Do you understand what I said? Okay. So in this pipeline, the processor design, as you can see, the write to register port is directly connected to the output of instruction fetch and instruction decoding pipeline register. Okay, so we can write like this. So this means that this is the instruction data, but this instruction data is an output of instruction fetch and instruction decoding pipeline register. It is because if we just see the pipeline register looks like this, DQ and clock. So this is the input and this is the output, and the output data is sampled by this clock signal. Okay. So this is the instruction output from the instruction fetch and instruction decoding pipeline register. At which clock timing? So if we just start the instruction fetch operation of the load instruction at clock cycle number 1, then this instruction output from the instruction fetch and instruction decoding pipeline register is generated at the start of the clock cycle number 2. Okay, but the write back of this load instruction is performed at clock cycle number 5. Understand? So actually the write register number is generated at clock cycle number 5, but it's a 3, 4. The data is out at clock cycle number 5 because the timing is different. If the timing is different, then this write to register number will be the write register number of the next instructions, not this load instruction, because the timing is different. So this is the past value, but the result of the load instruction is generated at clock cycle number 5. This is the future. So because the timing is different, in this design, this result of the load instruction is returned back to the incorrect register location. Understand? So how can we match the timing of the write to register number and the result of load instruction? It's simple. You can just delay the write register number. Okay. So because the write back of the instruction is performed during the write back stage, that is the clock cycle number 5 of the instruction, then we just need to delay. We just delay the required write register number for this result data, and then this write operation can be performed during the write back stage. Okay. So what does that mean? So actually, if you see this figure, the write to register number is here. The write to register number is sampled by this pipeline register, ID EX pipeline register. So at clock cycle number 3, this write register number is propagated to the EX stage. And then also clock cycle number 4, it's propagated to the memory stage. And then at clock cycle number 5, this write to register number is propagated to the write back stage at clock cycle number 5. And then at this time, the result of the load instruction is also generated, and then this will be returned back to the register file. So what does that mean? By propagating this write to register number to the next stages, then we can match the timing of write to register number and the timing of written data for load instruction. Okay. So when this data is written back to this write data port of the register file, this write register number is also given to the write register port of the register file. Okay, and then the timing is exactly matched to the data. So data is written back at clock cycle number 5. Also, by propagating write to register number to the next stages, then we can also match this written back register number at clock cycle number 5. Do you understand what I said? It's very important for pipeline the processor design. So we need to match the timing of data, and then we need to match the timing of control signals or the addresses or addresses or control signals of this data. If the timing is not matched, then the operation of this processor will be incorrect. So that means this is the very bad processor. If the processor generates the incorrect data, then this is a bad processor. No one will not use this processor. So in order to generate the correct data, then you need to remember that we need to match the timing of data and the timing of address or control signals. Okay, it's very, very important for pipelining processor design. And then many students are confused about the timing of data. Okay, so you need to understand, you need to try to understand the timing of each data when an instruction is executed inside of a pipeline processor. Okay. Okay, and then actually the story is the same, but the store does not perform the write back stage, but the write back stage is also consumed by store instructions. So one student actually posed a question on the Piazza, and why so actually the load instruction requires all 5 stages of the pipelining. But some instructions, such as R-type instructions, that do not require the memory stage. So that means we can complete these R-type instructions using 4 stages of pipelining, and then we can complete the load instructions using all 5 stages of pipelines. But that can be possible. But in this class, we are learning about very simple pipeline design, and then we are learning about the in-order processor. It's called the in-order processor. So in-order processor means that the instruction complete it's operation, their operations in order. That means the order of instructions. You know what I mean? So this is the load x1, 0, x2, and add x3, x4, x5. So these are instructions. And then, the add instruction requires 4 stages. And then this load instruction requires 5 stages. So if we just assign 4 stages for add instruction and the 5 stages for load instruction, then this add and load instruction will complete at the same clock cycle, right? Because the add instruction is the next instruction, very next instruction of the load instruction, but it requires 4 stages. So that means that it will consume only 4 cycles. The load instruction will consume 5 cycles. So what's the problem? So when the add instruction try to write its result to the register file, then at the same timing, the load instruction needs to write its result to the register file. But as you can see, our register file has only one write port. So even though the add instructions is completed at the same time, then we need to delay the write of this add instruction. Okay, and then another critical problem is that, okay, the load instruction may take the 10 cycles, 10 cycles. That means 10 stages or 10 cycles. So we need 10 cycles for completing load instruction. But this add instruction is requires only 4 cycles. Then let us assume that this is x1. So what's the problem? Even though what is the latest value for this x1? The latest value for x1 is the result of the add instruction. Okay, understand? But what's the problem? Because add instruction is completed earlier than load instruction, x1 is updated by add instruction, and then after some cycles, x1 is updated by load instruction. We need to avoid this situation. Why? The instructions are executed sequentially, then what the correct result of these instructions is the final result of x1 is updated by add instruction. But if the add instruction completes earlier than load instruction, then x1 the x1 may have the result of the load instruction after this after completing these instructions. Okay, that's the problem of out of order processing. And then we need to avoid actually this situation, because if the order is changed, then the incorrect result will be generated by instructions. Then we need to avoid this situation. So in this course, we will learn about the just very simple in order processor. So that means that every instructions complete in order. So we don't need to consider about this situation. Okay, that's why this add instruction also performs all 5 stages like load instructions. Okay, it's for better. So we are learning about the simple pipeline architecture. So every instructions pass through all stages of a pipeline process. Okay, so it's the same to the store instruction. Store instruction does not require write back stage, but this write back stage is also performed for store instruction. That means that just one clock cycle is consumed by the write back stage of store instruction. Okay, even though no operation is performed for this write back stage. Okay, I hope you can understand. And this is the multi-cycle view of the pipeline processor. So you can find that multiple instructions are executed this order. So instructions are executed sequentially and every clock cycle. So in the clock cycle by the clock cycle number, you can find that which instruction is in which stage of pipeline processor. So in the clock cycle number 1, then you can find that this load instruction is in the instruction fetch stage of this pipeline processor, and then the clock cycle number 2, then you can find that the load instruction is in the ID stage, and then the sub instruction is in the instruction fetch stage of the pipeline processor. So this is the multi-cycle view of the pipeline processor diagram. So we can also use this very simplified rectangular flow of instructions. Okay, and then if we just focus on the single cycle pipeline diagram, so then this diagram just shows which instruction is located in a certain clock cycle. So it's actually at the same clock cycle, the load instruction is in the write back stage, and then sub is in memory stage, and then add instruction is in execution stage. Another load is ID in ID stage, and that add instruction is in instruction fetch stage. So single cycle pipeline diagram just focus on how instructions are assigned to each pipeline stage during one clock cycle. Okay, so then what is missing? The control signals are missing. For this pipeline design, we just define the required data path elements, that is the hardware components for each operation step of instructions. And then we just insert pipeline registers between 2 adjacent steps. What is missing? Control signals. So our data path elements require control signals. So this leg write is the control signal for the register file, and then ALU also receives the ALU. The ALU control unit receives the ALU OP signal, and then ALU operation is ALU received the ALU operation. Also, you can find this multiplexer received the ALU source, and then mem write, mem read, then PC source. Then, like the control units of a single cycle processor, we need to connect these control signals. And how? Actually, same. The single cycle processor, control unit is here, and then instructions are given to this control unit. Okay, CU, and then we learned that inst from 6 down to zeros are given to this control unit, and then control unit generate some control signals such as the branch and the reg write ALU source and the mem read, mem write control signals. Okay, then how can we connect these control signals? And then in the previous slides, I mentioned that we need to match the data and control signal timings. So timings of data and control signals. Okay, so how can we match these timings? Like the write to register number of load instruction and the result of load instruction, we can also propagate these control signals via pipeline registers in order to match the timing of control signals. Understand? So what does that mean? So this is the control unit, and then instructions are given to this control unit, and then control signals are generated. So for example, reg write. So when this reg write control signal is required, instruction fetch, instruction decoding, EX, memory, write back. From 1 to 5, which stage? Please answer. Okay, it's 5. Why? This reg write signal is required at write back stage. Why? The write back to reg is controlled by reg write signal. Okay, so when the write back is performed at the write back stage, so that means that reg write is required at write back stage. It's the same to the write to register number. So how can we? So this reg write signal is generated by this control unit, but in order to use this reg write signal, this reg write signal is also propagated to the next pipeline stages along with this write to register number. So that means this reg write control signal is propagated until write back stage. Understand? Because reg write is required at write back stage. So how about the ALU source? ALU source is required at EX stage. So this ALU source is propagated to the EX stage via ID EX pipeline register. So 1 clock is delayed. So this is the low, not low, some deal, not deal, it's a it's a law. So control signals should be propagated until the control signal is consumed. So that means that because the leg write is consumed at write back stage, this leg write signal should be propagated until write back stage. And then with the same manner, ALU source is consumed at execution stage. That means the ALU source is propagated until EX stage. The other control signals like mem write and mem read, also mem to reg, are the same. How about the mem to reg? So mem to reg is required, that means that consumed at write back stage. So mem to reg are also, mem to reg is also propagated until write back stage. So just to remember this. So we need to match the timing of data and control signal, or we need to match the timing of data and addresses in the pipeline the processor design. It's very critical and it's very important. Okay. So this is the final pipeline design. Okay. As you can see, the control unit is here, and then control signals are also propagated via pipeline registers. Okay. So, and then you can see which control signals are consumed at which pipeline stages. Okay. Okay. Actually, the timing is the very important. Okay. And then many students struggle to understand when the signals are required and how the signals are propagated via pipeline registers. Okay. Okay, so I'll start here a little bit late. So if you have any do you have any questions? Okay, so if you have any questions, then you can post your question, or so I will also, you can ask questions after class. Okay, so thank you for your attention, and then see you in the next class.